Hello everyone, welcome back to Nated Engineering. Today we are doing an exercise on nozzles, power machines and 6. The exercise that we are doing is an exercise that I have taken from my textbook and it reads as follows. A gas in a convergent divergent nozzle expands from 500 kilopascal to 143 kilopascal. The initial temperature is 537 degrees Celsius and the adiabatic efficiency of the nozzle is 92%. Assume that all losses take place after the throat of the nozzle and that gamma is 1.4. The gas constant, which is R, it's 288 joules per kg Kelvin, and Cp, which is the specific capacity at constant pressure, it equals to 1008 joules per kg Kelvin. Calculate the throat and exit areas of the nozzle per kilogram of gas per second. This is the information that we are given. We are dealing with a convergent divergent nozzle. That's the first thing that we have to know. We have P1, T1. We have P2. We're not given T2. We're not given P of the throat and the temperature of the throat. And then we're given the adiabatic efficiency. We're given gamma, we're given the gas constant, we're given specific capacity at constant pressure, and then we were told to calculate for the areas at the nozzle and at the exit per kilogram of gas per second, which is our mass, 1 kg per second. So we know area. Let's start with C. It's given by what? V, which is our volume, divided by C. So what we have to do now is to calculate for the value of V and the value of C for us to be able to get the area. We know to get V, we're going to use MRT. PV. We have to use C. We have the mass, we have the gas constant, we are looking as PV. We are looking for this velocity, this volume. We have to get the temperature and the pressure since we do not have both. So we are going to start with pressure. We know PC is given by P1 times 2 divided by gamma plus 1 raised to gamma divided by gamma minus 1. So what is the value of P1? It's 500 kilopascal. 2 gamma is 1.4 plus 1 1.4 divided by 1.4 minus 1, and then here we are going to get our answer as 264.14 kilopascal. Then the next step is for us to get the value of TC. We know the formula to calculate for TC is given by what? TC is equals to T1 times 2 gamma plus 1 close bracket, and then we substitute 810 times 2 1.4 plus 1, this is 1.4, and then our answer is 675 kilo. Then from here we can be able to calculate for our area at the throat, which is given by the volume. Now we first need to calculate for V, MRT. It's equals to PV. We still need to get this. It's C, and it's C. Our volume at the throat is given by MRTC divided by PC. 1 meters per second. The value of our mass is 1 kg. Gas constant is 0.8 288. Our temperature, it's 675, and our pressure is 264.14, 264.14, and then we are going to get our volume as 0.736 meters per second. It's cubic meters per second. Now we have the volume. We are going to calculate for the velocity. Velocity cc is given by what? It's 2 times specific capacity at constant pressure times 10 to the power 3 in bracket T1 minus Tc. 2 times what is the specific heat capacity? It's 1.008 times 10 to the power 3. Temperature number 1 we are given as 810 Kelvin. Here in these formulas you will only use kelvins, and then here the temperature of the truth is 675. That will give us our velocity as 521.69 meters per second. It is then that we can now come to this formula and say the area at C at the trough is given by what? Volume of the trough divided by the velocity. Our volume is what? 0.736 divided by 521.69, which would give us 0.00141 meter squared. And that's how we get the first part of the question. We are also asked to calculate for the volume where at the exit or the outlet. So the volume at the outlet, the area at the outlet, it's equals to volume number 2 and velocity number 2. Remember, we're told about the adiabatic efficiency, and we're told that we are to assume that all the losses take place after the trough. So when we're dealing with this one, we have to take this one, the adiabatic efficiency, into consideration. So we're going to start. First, we're going to calculate for V. We know it's given by M R T. It's equals to P V. We will be using number 2, and number 2. On this, we have what in this case? We have the pressure, but we do not have the temperature. So we have to calculate for the temperature first. T2 is equals to T1 in bracket P2 divided by P1 raised to gamma minus 1 divided by gamma. And the temperature that we're calculating for here, we are not taking into consideration what the efficiency of the machine. Therefore, we are going to have the value of the temperature that we got here being the theoretical one. We can put it as T2 prime. So we will say from here we substitute 810, 143, 500, 1.4 minus 1 divided by 1.4, which will give us 566.449 Kelvin. And then we are going to come here after that and say T1 minus T2. T1 minus T2 prime. That's the formula to calculate for the adiabatic efficiency. We are given the adiabatic efficiency as 0.92. T1 we have T1 is given by 810 minus, this is what we are looking for, the temperature after the temperature at the outlet when we're taking into consideration the efficiency. So we are given what? T1 we have minus, this is what we just calculated for. Then we solve for this and got that our temperature number 2 is equals to Kelvin. This is the temperature that we're going to use to calculate for our volume given by MRT PV. We're dealing with number 2. We're looking for P for V. It's MRT divided by P. V2 1 times 0.288 times temperature number 2, it's 585.933, and then pressure number 2, it's 143 kilopascal. And then I got that my answer is equals to 1.18 cubic meters per second. So from here we now need this, the velocity. No, velocity is given by the square root of 2 times specifically capacity at constant pressure times 10 to the power 3 in bracket T1 minus T2, because now we're dealing with the outlet. 2 times the specific heat capacity at constant pressure, 1.008 times 10 to the power 3. Temperature number 1 is equals to 810 minus temperature number 2, which is 585.933, and this is equals to 672.1 meters per second. Then from here we can come to that formula to calculate for what? For the area. Area, it's given by what? The volume. Where's the volume? This is the volume. 1.18 divided by what? The velocity, which is 672.1, and this will give us 0.00178 meters per second, meter squared. That's the volume, meter squared. And then that's how we go about answering questions, this particular question on nozzles. I will see you on the next one.